So, this will imply the following theorem. As a consequence, you see the following theorem, which is basically going up theorem, theorem 1. Let A is a subring of B, B is integral over A, let P be a prime ideal of A, then there exists a prime ideal Q in B such that Q contraction equal to P. So, Q contraction means Q intersection B A. So, in other words, spec B to spec A, this map is surjective. Proof. See, you have this diagram. So, A, B is a subring of B. So, A to AP you have a map, and B to BP you have a map. So, now so you take a maximal ideal. So, let N in BP be a maximal ideal. So, consider M equal to N intersection AP. Now, because this is integral and N is a maximal ideal, so N intersection AP should be the maximal ideal, which is PAP. Right. So, now if you take, what is the pullback here? So, let us give a name. Okay, let us give this name is alpha, this is beta. And consider Q to be beta inverse of N, and P is the alpha inverse of M. Now, this diagram commutes. So, here when you pull back, when you take the inverse image of the maximal ideal, so if you call it Q, and then if you take under this map, if you take intersection with A, then you get P back. So, then what does it imply? So, from the diagram commutativity, get the Q, when you intersect with A, it has to be P. Right. So, this says that this map spec B to spec A is surjective. Right. Okay. So, now as a corollary, you see it is going up theorem. So, I will state it more elaborately. Maybe in the next page I will go. So, this is continuing. Going up. So, what is the statement? This is a going up theorem is known as going up theorem. So, let A is a subring of B, B is integral over A, and let P1, P2, Pn chain of prime ideals in A and Q1, Q2, Qm, a chain of prime ideals in B such that first is that m is less than n, and second condition is that if you take Qi intersection A, you get Pi. That is Qi contraction is Pi. Then you can extend the chain Q1 up to Qm to Q1, Q2, Qn such that Qi intersection A equal to Pi for all I equal to n. Then the chain then star can be extended to a chain of prime ideals in B such that Qi intersection A equal to Pi for all I equal to 1 to n. See, the point is that by going to the quotient, the integrality does not change. So, that will say that without loss of generality, we can assume that n equal to 2 and m equal to 1. Because when you have right? So, without loss of generality, we can assume proof. Since by quotienting the integrality property does not get changed, remains unchanged. Without loss of generality, we can assume n equal to 2 and m equal to 1, right. So, now once you agree, then you so you have a chain P1. So, we have P1 in P2 in A and Q1 in B such that Q1 intersection A equal to P1. So, I want to produce a Q2 such that Q2 intersection A equal to P2, right. So, consider A bar, which is A mod P1, and B bar, B mod Q1. So, we have A bar inside B bar, and we know that B bar is integral, and this B bar is integral over A bar. Now, P2 is a prime ideal in B. So, you consider the image of P2, which is P2, which I denoted by P2 bar. So, P2 bar is a prime ideal. Sorry, P2 bar is the image of P2 in A bar. So, P2 bar this is image of P2 in A bar. P2 bar is a prime ideal in A bar. Right. Now, B bar is integral over A bar, and this is a prime ideal. So, now by the previous theorem, there is a, so by previous theorem, by theorem 1, there exists a Q2 bar in spec B bar such that Q2 bar intersection A bar equal to P2 bar. But this is same as saying that Q2 contains Q1 because B bar is nothing but B mod Q1 such that Q2 intersection A equal to P. Right. So, if you have a chain in spec of A, and so you can complete it. So, this is, that's why it's called going up theorem. Okay. Now, we will see that in the next class that opposite also it's true. Suppose you have chain, suppose n is less than m. That means, if you have a chain of A is in, B is integral over A, and if you have a chain of prime ideals in A and chain of B prime ideals in B, such that Qi intersection A equal to Pi, then you can you can complete the chain in A such that chain of prime ideals in A, that means P1, P2, Pn to P1, P2, Pm, such that Qi intersection A is Pi for all I equal to 1. So, you can, that we will see, that requires a little bit more work. So, okay, so that we will see in the next class, not today, not today. I need to introduce some more, not very difficult, but yeah. Okay. So, but before that, I need a very important result. I don't know. Maybe I'll lead. This is quite important. So, let B A is a subring of B, and C be the integral closure of A in B. So, that means C is set of all elements of B which are integral over A. That is called integral closure, right. So, C, so let S be a multiplicatively closed set closed subset of A. Then, if you know that C is the integral closure of A, then S inverse C is the integral closure of S inverse A in S inverse B. So, we already know that if C elements of C are integral over A, so S inverse C is integral over S inverse A, that is fine. But this is saying more. That means there are no elements in S inverse B which is not in S inverse C which are integral over S inverse. So, proof is proof. So, by previous results, I think proposition, I have my notation is proposition 1, 2, I think. If you go back, you will see this. S inverse C is integral over S inverse A. So now you have to prove what? Now suppose you have some element which is integral over S inverse A, you have to say that it is in S inverse C. So now suppose B by S belongs to S inverse of B integral over S inverse A. I want to prove that B by S is actually in S inverse C. So that means the B by S will satisfy some equation like B by S power n A1 by S1 B by S power n minus 1 dot A n by S n, right? Where AI's are in A and SI's are in S. SI's are in S. So now you consider T, which is S1, S2, Sn. And multiply the equation star by St power n. Right. If you multiply, then you will see that you will get something, the equation will become like Bt power n plus A1 St by S1 Bt power n minus 1, something like this, A n St power n by Sn equal to 0. But see, S is nothing but S1, S2, Sn. So when you divide S by S1, so then S1 divides S, right? So then all these coefficients are in A. This is also in A. So this implies, so all these coefficients of Bt power, so this implies that Bt is integral over A, right? So if Bt is integral over A, that means Bt is in C. So this implies that Bt by St is in S inverse C.
Sir, how these elements are in A? How these coefficients are in A?
Because when you take this A1, T is what? S1, S2, Sn. So if you see numerator, you have some power of T. And downstairs, what do you have? A denominator, you have SIs. So this SI will get cancelled. Okay. So but Bt, now Bt is in C. So Bt by St is in S inverse C. But Bt by St is nothing but B by S in S inverse C. But this is same as B by S. So that means, so S inverse C is a integral closure of S inverse A, right? So these are done. Okay, I think I am almost done. So I will stop here.